This is Unit 10B, and in this video we'll be talking about the radius of convergence. So why is it important to know that we can write this? Why is it important to know that we can write this infinite series to represent the sine of x? Well, basically it's this. Our trigonometric functions lack finite algebraic formulas. Okay, so power series are the next best thing. Now, using power series allows us to find approximate but very accurate values of trig functions as well as other functions. So let's go ahead and see how this works. Use the Maclaurin series for the sine of x to approximate the sine of 1 so that the error in your approximation is less than 1 over 1,000 without using your calculator. And then justify that your error is less than 1 over 1,000. Okay? So let's go ahead and give this a try. If you'll remember, the Maclaurin series for the sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so forth. Okay? So if we're going to approximate the sine of 1, everywhere there's an x, we're going to put a 1. So we have 1 minus 1 over 3 factorial plus 1 over 5 factorial minus 1 over 7 factorial, and so forth. Okay? Let's simplify that. 1 minus 1/6 plus 1 over 120 minus 1 over 5,040 plus ... And we could go ahead and we could continue on. But let's see where we're at. If we want our error to be less than 1 over 1,000, that's this term. So that will be the bound on our error. So we will cut our approximation off right there. So we can say that the sine of 1 is about equal to 1 minus 1/6 plus 1 over 120. Now, we justified it without our calculator right here. Okay, here was our justification. Now, what I want to do is, let's do here. Let me change that. This is with no calculator here. Now we want to justify, and we can use a calculator now to justify. So we can say that the sine of 1 is about equal to this. And actually, if you put that together and get a common denominator, you get 101 over 120, and that's about equal to 0.84166. Okay? So now what could we do? We could use our calculator to find the actual error in our approximation. Okay? So the sine of 1 is actually equal to 0.84147. Let me show you that. .84147, and our approximation was 101 divided by 120, and so we could go ahead, since it's the absolute value, we can subtract either one. I can subtract that value, and I would get this error. Okay, so let me go ahead and get that written down. The absolute value of our error is going to be 0.84147 7 minus 0.84166, and that error, you can see it in the calculator, 0.000196. Pretty amazing. Pretty amazing. Okay, let's go ahead and take a look at this next question. Find in series form this time an antiderivative for the sine of x squared, and then use it to approximate the integral from 0 to 1 of the sine of x squared, so that the error in your approximation is less than 1 over 1,000. And this actually says without your calculator. So first things first, let's go ahead and write the sine of x squared. And that's equal to x squared. And you can see here that we have the sine of x right here. So everywhere there's an x, we're putting an x squared. Minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial. And if I have to put a few more terms in there, I will. So that's the sine of x squared. Now they've asked us to integrate that. So we have the integral from 0 to 1 of the sine of x squared dx. And let's begin. I'm going to put a bracket because we'll evaluate that from 0 to 1. And we have 1/3. Why don't I write it like this? X cubed over 3. That's 1/3 x cubed. Minus, don't forget to leave these constants alone. And then we have 1/7 x to the 7th. And then let's leave that 5 factorial alone. And we have x to the 11th divided by 11 minus x to the 15th divided by 15 times 7 factorial, and so forth. And we are going to evaluate that between 0 and 1. Now, that's just equal to 1/3 minus 1 over, and this is a good time to put 42. 7 times 3 factorial is 42. Plus, and we have 1 over 11 times 120 minus 1 over 15 times 7 factorial. I won't do any of that now. Now, if we would plug in 0 here, we would have 0, okay? So we could just leave it like that. And then let's take a look at this error. We have 1/3 minus 1 over 42. And if you notice, this denominator is definitely less than 1,000, okay? So we actually are going to cut it off right here. So this is equal to 13 over 42, okay? So what can we say? We can say that the absolute value of the error is less than 1 over 11 times 120, which is less than 1 over 1,000. And that's by that remainder boundary. It is a bound on our remainder. Now they want us to use our calculator to find the actual error in our approximation. So don't forget, this is our approximation. 13 over 42 is our approximation. So let's see what we have here. The integral from 0 to 1 of the sine of x squared dx is equal to, so we can go ahead and bring this over here. So we can have math 9, and we're going to integrate from 0 to 1 of x squared. And we get point, did I do that right? Oh, I didn't do that right. I was going to say, we need the sine of x squared. There we go. And we get 0.310268. So we have 0.3102683. We'll let our calculator keep all of those decimals. So the absolute value of our error is going to be equal to, and let's take 13 and divide that by 42. And let's see, I did 3. 13 divided by 42, and we would get 0.3095. Okay, so, and 13 divided by 42 is 0.3095238. Okay, so that error would be 0.3102683 minus 0.3095238. And let's go ahead and subtract that. So we would have this value minus that value. And as you can see, we were very, very close. 0.000745. And I'll just put 4 dot, dot, dot. How about that? So that is the actual error in our approximation. So as you can see, we are getting very, very close. Using this method, we are getting very, very close to the actual value. Okay? Now, let's go ahead and look at this next example. Write the Maclaurin series for e to the x and give the first 4 non-zero terms and the general term. So this is actually sort of a review. We have e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, dot, dot plus x to the n over n factorial plus dot, dot, dot. Okay? That's e to the x. Now, use your answer to part A to find the limit as x approaches 0 of f of x minus 1 divided by 2x. Okay, so that's the limit as x approaches 0. And we have 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, 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 all minus 1 divided by 2x. And as you can see here, our 1's will cancel, and we will have 1. So the 1's cancel, and we will have the limit as x approaches 0 of x plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, 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 all divided by 2x. So we have the limit as x approaches 0. And as you can see, you're going to get 1/2 because we have x divided by 2x. Okay? And now we will divide this term and this term. But what do you notice? The next term is going to be x divided by 2 times 2 factorial plus x squared divided by 2 times 3 factorial. And what's going to happen when you're actually looking at the limit of each one of these? All of these terms are going to go to 0 when you take the limit. So this limit is equal to 1/2. Okay, let's take a look at these geometric series. Now keep in mind, geometric series are formed by multiplying by a common ratio r. And we've talked a lot about r. And a geometric series can be written in this form when n is equal to 0, or one of my favorite forms, if n equals 1 to infinity, we have ar to the n minus 1, okay? If you begin at 1. So either one of these forms, ar to the n, if you begin at n equal to 0. Suppose I told you to start with a equal to 2 and let r equal to 3. What geometric series would you write? Okay, well, a is 2, so I'll start with 2. And if r is 3, I'm going to multiply by 3 each time. Dot, 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 plus a r to the n. And you could say that that started with n equal to 0. That's fine, because this is what they gave us to use. What if a was equal to 2 and r was equal to negative 3? Okay, 2. And then this would be a negative 6 and a positive 18 and a negative 54 and so on and so forth. And we'd have a r to the n. And what if a would be equal to 1 and r would be equal to x? We would have 1 plus x squared plus x cubed plus x to the n. Look at that. So now we can use our knowledge of the geometric series to help us write a power series for a function if the function can be written in this form, okay? So if the function can be written in a over 1 minus r form, we will then write a power series for a function. So let's review this. A geometric series of the form sum n equal to 0 to infinity, ar to the n, converges to the sum s equals a over 1 minus r, where a is the first term and r is the common ratio. Now, that is only the case if r is less than 1. Absolute value of r is less than 1. If the absolute value of r is greater than or equal to 1, the sum does not exist. So we can only write the sum if that common ratio r is less than 1. Let's go ahead and take a look at this. Find a power series for f of x equals 1 minus x squared centered at x equal to 0. Give the first 4 non-zero terms and the general term. For what values of x does your series converge? Okay, so one thing at a time. The first thing I need you to know is to know this. 1 over 1 minus x is equal to this series, n equals 0 to infinity, of x to the n. And that's equal to 1 plus x squared plus x cubed, and so on and so forth. Okay? That's what this is equal to. This geometric series is equal to 1 over 1 minus x. Okay? Only if it converges. Okay? Okay, so what could you say? 1 over 1 minus x squared is equal to the sum, n equals 0 to infinity, of x squared to the n. So our x is x squared. And we could say that that's equal to 1 plus x squared plus x to the 4th plus x to the 6th, and so on and so forth. And this is actually equal to n equals 0 to infinity, x to the 2n. Because it looks just like that. So the series converges when the absolute value of x squared is less than 1. Because this series, and I could probably write this here. It is true if it converges, but if the absolute value of x is less than 1, because remember, x is our radius. Just like here, it converges if the absolute value of r is less than 1. Okay? So that's this x, and that's this x. Okay. So this time we had x squared. So now what we can have is we can drop the absolute values, and this will occur when -1 is less than x is less than 1. Okay? And you could actually just do that, just knowing that. Or you could put or -1 to 1. Okay. On the calculator, we're going to graph 1 over 1 minus x squared. And then we're going to let y2 be the first 5 terms of the series we found. And trace that on a graph from x equal to 1/2 to x equal to 2. And what I would like you to see is this. Okay, so press your y equals. And in y1, we'll put 1 divided by 1 minus x squared. Okay, and then on the next one, we'll go ahead and put 1 plus x squared plus x to the 4th. And how many did they want? The first 5 terms plus x to the 6th plus x to the 8th. Okay? And we're going to just zoom 6 first, and then I will zoom in. Okay? And so what do you notice? Do you see that both curves here are about the same? Only when x is between what? When x is between -1 and 1. So you could press trace and press a 1. And you could see that when x, you could see that right here. They're not doing a very good job here. Okay? There's 1 right there. So these graphs look very, very much alike, except when you go beyond that interval. So let's just make a note. This calculator does not do the best job here. If you can see when x is and not doing a very good job. But I'll go ahead and write, and you can please try that on your calculator. I really need to get another calculator. But let me just write down what you should see. You could sort of see it on that. Okay? Y1 and Y2 looked a lot alike. looked alike when x was between 0 and 1. But at x equal to 2, the curves are very different. So you could really see when we moved out of that center part, when we went beyond, it looked like even at about x equal to 0.7, it started to change, okay? So let's go ahead and take a look at this. Find a power series for f of x equals 12 over 4 plus x, centered at x equal to 0. Give the first 4 non-zero terms and the general term. And then we're asked, for what values of x does your series converge to f of x? Well, remember, everything is going to be compared to 1 over 1 minus x is equal to n equals 0 to infinity of x to the n. And remember, this series converges when the absolute value of x is less than 1. So everything we are doing, we are going to be comparing to this series, okay? So what did they give us? They gave us 12 over 4 plus x. How can I get it to look like this? Well, let's first take the 12 out and see what it looks like now. We have 12 times 1 over 4 plus x. Well, what if now we divided that denominator by 4? Okay, or how about this, factored out a 4? Let's factor a 4 out of that denominator. I would have 1 plus 1/4 x. Okay, now I'm getting close. I need a minus sign there. So I will have 3 times 1 over 1 minus a negative 1/4 x. So it's all manipulating. So what do you notice? Our x is, our x is negative 1/4 x. This is their x, that's our x. So how can we write that? We can say that that's equal to 3 times the sum n equals 0 to infinity of negative 1/4 x to the n power. We're comparing it to that with our x, okay? And then let's just write it a little bit more like the forms that we see. So that's equal to the sum n equals 0 to infinity. And we'll bring that 3 in. And then we have a negative x over 4 to the n. Now we're getting there. We want to get that negative 1 to a power out of there. So we have negative 1 to the n times 3 times x to the n all over 4 to the n. So you should convince yourself of that. And then this will converge. The series converges when the absolute value of our x, which is negative, the opposite of x over 4, we could even put 1/4, let's just put what we had earlier, negative 1/4 x is less than 1, okay? And, I mean, that's it. You could just say this, or you could say the opposite of x over 4 is less than 1, the absolute value. Our radius of convergence, r, is going to be equal to 4. And our interval of convergence is going to be between negative 4 and 4. Okay? So, yeah, I think that you'll do okay there. Okay, let's try one more of these. Find a power series for f of x. And by the way, this absolute value here, you can have the negative come out, and you can have the absolute value of x all over 4 is less than 1. So the absolute value of x is less than 4. So x is on that interval from -4 to 4. I hope that helps. Okay. Find a power series for 5 divided by 4 minus x. Remember what we're doing. We are comparing this to 1 over 1 minus x. And if you practice writing this, you won't forget it. N equals 0 to infinity of x to the n. And this series converges when the absolute value of x is less than 1. All of that comes from a geometric series. Okay, let's do it. So we have 5 over 4 minus x. Let me just put this little zigzag like I did last time. Is equal to, so we're going to start manipulating, 5 divided by 4 minus x minus 3 minus 3. Now let's take a look at this. This is a little bit confusing. We needed to use this 4, okay? And we're trying to get some sort of term for x, but we need a 1. So a 4 minus a 3 gives us a 1. So sometimes that's nice. Let me give you a little hint. Leave the 4 alone and then turn the 4 into a 1 by subtracting a 3, and then make up for that by subtracting the opposite. We need the minus right there. Okay, it'll just take some practice. Okay, so that's equal to 5 divided by 1 minus x minus 3. So look at this. Our x is x minus 3. So let's go ahead and write this. And this question asked us to give the first 4 non-zero terms, a little bit different than this one. Well, no, we gave, I think we might have forgotten to give the first 4 non-zero terms there, but we could write them. We did the general. So let's go ahead and do that. That's equal to 5 plus 5 times x minus 3 plus 5 times x minus 3 squared plus 5 times x minus 3 cubed plus dot, 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 5 times x minus 3 to the n, dot, dot, dot. So that is a power series centered at x equal to 3, and our first term was a, so a was 5, okay? So you could say this right here is equal to a over 1 minus r. A is equal to 5, and r is equal to x minus 3. Okay, so that's where we get a, and then we have our first r and r squared, and of course we still have our a there. So this is ar squared, and so forth. Okay. And so forth, okay? So now, when will this converge? This series converges when the absolute value of x minus 3, because that's our r, is less than 1. So we have when x is between 2 and 4. So our interval of convergence is 2 to 4, and our radius is 1. Okay, now we don't check endpoints on a geometric series because we only converge when we are less than, okay? So it does not say less than or equal to. So it's super important. That's why we don't check endpoints, okay? Okay. So let's just look at a couple more here, and then we will resume in another video. Since the sum of 1 plus 3 over 1 factorial plus 9 over 2 factorial and so forth, find the sum, okay? Well, this should look a little familiar since e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so forth. This series is e cubed, okay? As you can see, everywhere there's an x, we have a 3, okay? And so, you can see here that the sum is e cubed. Okay, let's take a look at this one. Just take a good look at it. You can also take a look at this. Should be reminding you of one of the series. Since the sine of x is equal to x minus x cubed, so we have odd factorials, that should be a hint, plus x to the 5th over 5 factorial, negative 1 to the n, x to the 2n plus 1, all over 2n plus 1 factorial. This series is the sine of 2. So as you can see, everywhere there's an x, we have a 2. Okay? So what could we say? Therefore, the sum is equal to the sine of 2. Okay? Find the sum of this series. The first thing you should notice is that we have a geometric series. These are super important. You might even be able to see it from here to here. Each numerator is multiplied by 2. Each denominator is multiplied by 3. Right away, you can also see it here, okay? So A is equal to 1 and R is equal to negative 2/3. Since the absolute value of R is less than 1, the sum is A over 1 minus R, which is 1 over 1 plus 2/3, and that's equal to 5/3. And that concludes this first part